continuation of the 1-2 notes. This brings us with example 3. We are going to graph f of x is equal to the absolute value of x with our domain of -4 to 4, and then we are given that g of x is equal to 2f of x. So the first thing that we're going to do is graph the original function that we have, that's f of x. And by doing that, notice that I expanded the domain a little bit from what I had given you on the previous table for the parent function of absolute value, because this domain does go from -4 to 4. So I'm only using 5 of the points. We have -4, 4, -2, 2, 0, 0, 2, 2, and 4, 4. In the table from before, I only went from -2 to 2, but typically the absolute value function does keep expanding. So you can expand it out as far as you need to for whatever domain that you've been given. Now, we are given that g of x is equal to 2f of x. That means I am taking all the f of x values, which you can see here are the y values, and I am multiplying them all by 2. So for this first one, my g value is going to be 2 times the f value, which is 4. That's going to give me 8. That's going to be a new point of -4, 8. And that's going to be right up here. The next one will be 2 times 2, so that will give us 4. That's a new point of -2, 4. Next we have 2 times 0, which is 0. That's going to be the point 0, 0, so that point is actually going to be the same. Then I have 2 times 2, which is going to give us 4 again. That's the point 2, 4. And then lastly, 2 times 4, which is 8. That's the point 4, 8. So you can see here, when I draw in my blue section, we have a question here, how are the domains and the ranges related? Well, the domain of the black and the domain of the blue are actually the same thing. So the domains are the same. They're both going from -4 to +4 on the x. However, for the range, the range of f is from 0 to 4. The range of g goes from 0 to 8. That should be a bracket instead of a parenthesis. So notice that the range of g is actually twice as big as the range of f, which makes sense because I have this 2 multiplied on the outside. When you multiply the function by some number, you are actually stretching it in the horizontal direction. So you're going to be increasing the range. Both of the slopes here are going to be much more steep than they are with the black parent function. So this was a stretch. It's some transformation that increases the distance between your points by a given factor. So the example we just did has a vertical stretch by a factor of 2. You can also stretch on the horizontal, but to stretch on the horizontal, you have to be acting on the x value inside of the parentheses. And that actually would have to be some type of fraction because you'd have to widen it instead of making it more narrow. There'll be a summary page coming up here in a bit that you can see all of this. So now we have example 3b. We're going to graph the same parent function. So I'm going to use those same starting points. -4, 4, -2, 2, 0, 0, 2, 2, 4, 4. So there's my parent function. And I am going to label this f. In the previous one, I don't think I actually went through and labeled that. So here's my x, my f of x. And I'm not actually going to put in the points that we have yet, and you'll see why. H of x is f of 2x. And then finally, we have our point x, h of x. Now, the thing that you have to be careful of here is the fact that h is equal to f of 2x. We still have to keep in mind what the domain is of f. The domain is -4 to 4. So if I look at my x value of -4, which is where I start from, if I multiply that value by 2, I get -8. And I can't find f of -8 because -8 is not within the domain of f. So you need to think about what x value that you could multiply by 2 would be within the domain. The first one that happens at is -2. So our h value is going to equal f of 2 times x. So that says f of 2 times -2, which is f of -4. And according to the original function, f of -4 is equal to 4. So this is the ordered pair -2, 4. It's going to be right there. We could also do -1 because I can multiply -1 by 2 and get -2. But I'm going to skip that one. I'm only going to do 3 points so we can get a good picture here. So I am going to do 0 because 2 times 0 is f of 0, and at 0 we get 0. So this point also does not change like it didn't change in the last example. Then I'm going to jump up to 2. F of 2 times 2 is f of 4, and that was equal to 4 in the original function. So this is the point 2, 4. So this is my h. So just like in the previous example, or if I was trying to use -4, I can't use +4 because if I multiply +4 by 2, I end up with +8, and +8 is not within the domain for f. So that's one I would have to skip, just like I had to skip the -4. Now when we compare the domains and ranges, with these ones, the ranges are the same. They're going from the same y value, same bottom y value, same top y value. But what changes about this one is the domain. Because the f domain is -4 to 4, but because I had to double the domain of h, the h domain only goes from -2 to 2. Since I was doubling the values in f, I still had to make sure that they fit within the original domain of f, and if I double just what f has, I'm not within that region. So I'm actually taking half of it by multiplying the x on the inside. This, if you notice, if we were to expand this out, we would actually get the same kind of graph that we had for the previous question, but this one is different because it acts inside on the x, then outside on the f of x. So this one, rather than being a vertical stretch like the previous question, this is a horizontal compression. Imagine if you were squeezing in from the sides, you would actually get the same result as if you were pulling up and down, but the force is acting in a different direction. So compression, that is going to decrease the distance between the points. This graph, again, like I said, was a horizontal compression by a factor of 2. It's going to look the same as a vertical stretch, but again, that force is acting in a different way. You can also have compressions and stretches on the opposite way, so you didn't have to have just the compression on the horizontal. You can compress vertically as well. That would be like a fraction acting on the y value. And you can also stretch horizontally. That would be like a fraction acting inside on the x. And all of that is summarized on this page. So you can see we have here vertical in the top. If you have a times some f of x, that's the top two things that we have here, and then horizontal down here. I'm going to scroll just a little bit so that my window view is not in the way. And then you can see all of that. Please make sure to maybe take a moment, pause this video, jot this down, copy it down from the notes that were uploaded to Schoology, because this is extremely important. When you are working through your IXLs on this section, they will distinguish between the vertical and the horizontal depending on where this A value is. Whether the A value is outside of the function or the A value is acting on the X value only. So please make sure you make the distinction between those. I guess there's some things that I need to go through and erase from previous classes. So rather than doing that, I'm just going to go through and talk about these. You can watch some of these in live time or work through them in Savas. If you'd like to do that, please just let me know. So we have two different transformations here, and I know this one is cut off by my video, but that's okay. The top one is A. We have y equals the negative of x plus 2. This blue function here is the original function. So that's what I'm taking. This is where I'm transforming my dots. Because there's a plus 2 inside with the x, that means I'm moving my graph to the left 2. The negative out in front means we're reflecting over the x-axis. So to get this red function, and again, the bottom of it does go down through where the video is here. I don't know if you can see if we scroll, I had to expand that a little bit. We would take this blue graph, I would move everything to the left 2, and then I would flip it down so that it's on the other side of the x-axis. For part B, that's the green function here. Again, I'm starting with the blue function. It says half of f of x plus 3. Half of f of x means we are taking half of the y value, and then we're adding 3 to the result. So I took all these y values in the blue function. I took half of them. For example, this one has a y value of 2. Half of that would be 1. And then I would move my graph up 3. So 1, 2, 3. That's where it puts me at this first dot. So all of these green dots, you look at the corresponding blue dot, you're going to take half of the y value and then add 3 as a result. And then you can get that green transformation. With this one, we were just looking at a couple of graphs and making, basically just stating how the blue graph turned into the red graph. The green dotted graph is the midway graph. So that would be doing one of the transformations. It's actually doing the one that's listed first. And then doing the second transformation would give you the final picture, the red one. So here I have a 1/3 on the inside. That is on the horizontal because it's inside acting on the x. And it's a horizontal stretch because it's a fraction. Then I have the negative on the outside. So first I did a horizontal stretch. That's how this blue graph got stretched out to this dotted green graph. And then we reflected over the x-axis. So we took that green dotted graph and flipped it down. For part B, the blue graph again is what we're starting at. I have the -4, so that means +4 is my h, 5 is my k. So we took this blue graph, we moved it to the right 4, so that's how we get the dotted green, and then we are shifting it up 5. And I know it looks like the red graph and the dotted green graph are different widths, but that's only because of how this graph is drawn and because the arrows end at the edge of the coordinate plane. They are actually the same width. There's just something to keep in mind with that. The last one that we looked at in this section is about a train ride. This is very similar to the diver problem that was in the section opening activity from 1-1. This is a function. We have time and distance from a station. So this train is making some kind of trip. Gets to a point at 15:15, which means in 15 minutes they are 15 kilometers from the train station, and then it's coming back to the train station. The entire trip took 30 minutes, so that means that 0 to 30 is my domain, because the train could spend 0 minutes traveling or 30 minutes traveling in a single trip. This function here is the basic absolute value function. That's what you're plugging into to get your equation. H and K, which I have circled here, well, I just circled there, that is going to be your vertex. So that is going to be your peak or your valley of your absolute value or of your quadratic, depending on if it opens up or opens down. To get the A value, there are a couple different ways you can do that. You can actually plug in the H and the K, and then an example of an X and Y, like you could use 0, 0 or 30, 0 as your X and Y, and you could solve for A. There is a shortcut though. For any absolute value function, the A is going to be the slope of the right-hand side. So this right-hand side, that's why I drew in this triangle here. To get from the 15, 15 to the 30, 0, I am going down 15 and to the right 15. So negative 15 over 15 gives me a negative 1, which is why I have this negative out in front here. For a quadratic, that value, that A value, is also the, quote, slope of the right-hand side, but you have to look in between the vertex and the next integer value. It will not work if you're going out further than one integer value away from where the vertex is. And if the vertex is not a whole number, that doesn't always work the way that it should. So just keep that in mind whenever you're working through this. Lastly, we did not do this try it, so don't worry about that. But there is a concept summary on page 20, and there's a lot to summarize in 1-2. The concept summary focuses on the translations, the reflections, and the dilations, making things wider, making things smaller, the stretches, the compressions. So that is something you can use as a reference. I hope this was helpful. Again, as I always say, if you have any questions on this, please feel free to contact me. We will be getting some less intense sections as we move through chapter 1. So just don't be discouraged if you're still struggling with this. Use the IXLs, use the MathXL to help you improve your understanding, and contact me if you have any questions at all.